Hi everyone, this is the notes for section 9.5, which is how to do proofs on the coordinate plane. So in this section, we're pretty much taking everything we know already from the rest of the chapter and using it to show that things are true if we're given ordered pairs. So we're going to be showing things like have congruent distances or lengths. If they have congruent lengths, then we use the distance formula. If we want to show that something's parallel or perpendicular, we find their slope. And then if we want to show that something bisects, we would use the midpoint formula. So here's all of our formulas that we've learned from 9.1 and 9.2. And then some things to remember about horizontal and vertical lines, parallel and perpendicular lines. Okay, so on our next page, we have a lot of tips on how to do these proofs, so let's go ahead and write those down. So if we're trying to show that triangles are isosceles, equilateral, scalene, then it would be using the distance formula because that's length. We use this, the distance formula to show length. If we want to show that it's right, we would have to have a right angle, so we would use slope to show that they're perpendicular. And then if we want to show that it's isosceles and right, we would use the distance and the slope formula. To show that something's a parallelogram, we have a couple different ways. One, if we show that their diagonals bisect, then it's going to be a parallelogram. So that'd be using midpoint. If the opposite sides are congruent, we would have a parallelogram. If opposite sides are parallel, or if one set is congruent and parallel. So remember, those are pretty much our main facts about parallelograms that we learned back in chapter 6. So now we're just going to do it on a coordinate plane instead of just being given a diagram. If we wanted to show that something was a rectangle, then if we had that their midpoints would show that the diagonals bisect, and then we would have to use the slope to show that the vertex has a right angle. Or we can use the distance formula to show that the diagonals are congruent, which would probably be the easier way. And then for a square, we can show that all the four sides are congruent using the distance formula, and then use the slope formula to show that it has a right angle. We'd have to do both because just having congruent sides wouldn't mean that it is could be a rhombus, or if it's perpendicular, it could be a rectangle. So you have to show both for that. Okay, so what I want you to do right now is pause your video and go ahead and graph all your points for the other examples that we have, those 4 examples, so that way they're all ready when we get to them. So pause, graph your points, come back, and we'll do the proofs. Okay, so for our first proof on page 2, it says to show that that triangle is a right isosceles. So if we wanted to do this, I like to make a checklist of what we need to look for. So what we would need for it to be a right isosceles is that it has to have 2 congruent sides. So after graphing it, you can kind of see that BC should be congruent to AC. So we would need to have that. Excuse me. And then we would need to have a right angle. So we would need that angle C is right. So to show that those sides are congruent, we would use the distance formula. So let's do that first. So for one, we would need to find the distance of BC and AC, and they would have to be the same to make it isosceles. So let's do the distance formula with BC. So remember from 9.1, you subtract the x-coordinates, square it, subtract the y-coordinates, square it, add them together. So we're looking for the points for B and C. So the x-coordinates be 1 minus 5 squared plus 3 minus 6 squared. So negative 4 squared plus negative 3 squared. So we get the square root of 25, which is 5. So we would have to get the same for AC in order for it to be isosceles. So let's try AC. So subtract the x-coordinates for A and C. So it'd be 1 minus 4 squared plus 3 minus negative 1 squared. So negative 3 plus 4 squared would be 9 plus 16, which is the same as up here, so we get 5. So that means that AC is congruent to BC, since they were both equal to 5. So we have part of this, so that means that it's isosceles, we just don't know if it's a right angle. Okay, so for the second part, we would need to show that it's a right angle. So that means that these two lines would have to be perpendicular. AC perpendicular to BC. Okay, so we need to find their slope. So let's count the slope of CB. So remember, it's rise over run. So from C to B, we would go up 3 and to the right 4. So that'd be 3 over 4. Now we'll do the slope of CA. So that would be going down 4 and to the right 3. So what did we have to have for two lines to be perpendicular as far as their slopes? Good, we need opposite reciprocals, which is exactly what we have here. They're opposite sides, positive and negative, and they're reciprocals. So that means, therefore, CB is perpendicular to CA. So we have that angle C is 90 degrees. So in conclusion, triangle ABC is a right isosceles triangle. Okay, so that's it for that proof. So we showed that they have congruent distances to make congruent lines, or equal distances. We showed that their slopes are opposite reciprocal, which gave us our right angle, and that was it. Okay, so let's take a look at our next example and see what's going on with that one. So for this one, we want to show that we have a parallelogram. So remember, we had our list of 4 different ways. So we have 2 problems that are actually asking us to show this. So for our first one, we're going to do one way, and our second one we'll do a different way. So we are going to use that the opposite sides are parallel for our first one, because that would make a parallelogram. So we would need that this line OL is parallel to NM, and then we would need that ON is parallel to LM. So we use our slopes. So we would need to find the slope of OL, the slope of NM, and then for part 2, we would need the slope of the other 2 lines, ON and LM. So remember, to find slope, we count rise over run. So if we're doing OL, we want to go from O to L. So we would rise 1, 2, 3, 4, 5, and run 2. So our slope of OL is 5 over 2. So now start at N and go to M. So we would rise 1, 2, 3, 4, 5, run 2. So those are congruent slopes. So remember, congruent slopes make parallel lines. So we know that OL is parallel to NM. So we got one set. So now we need ON and LM. So we rise 0 and we run however much, it doesn't really matter. So the slope is 0. Remember, horizontal lines have 0 slope. And the same is true for the other one. They're both horizontal. So that means that ON is parallel to LM. So that makes this a parallelogram. So we can say in conclusion that it is a parallelogram because opposite sides are parallel. Okay, so for our next one, we're going to try it a different way. These 2 are the ones that I like the best because they're the easiest, just counting slope. But this way, we're going to do the midpoint. So if their midpoints are congruent of their diagonals, then that means that their diagonals bisect. So we're going to look to show that the diagonals bisect. So that would mean that QS and RP share a midpoint. So if we find the midpoints of those diagonals, they should land at the same point. So let's first find the midpoint of QS. So remember, that is the formula where we add the x-coordinates, divide by 2, and add the y-coordinates and divide by 2. So make sure you're looking at the right points. So we're doing QS. So that would be 2 plus 4, and then the y is 4 plus 3. So we would have 6 over 2, 7 over 2, so we get 3.5. So midpoint of the other line, PR, we would set it up the same way. So add the x's, divide by 2, add the y's, divide by 2, and we'll simplify it. So for P and R, we have 1 plus 5 and 1 plus 6. So we get 6 and 7, just like we had up here. So the midpoint is 3.5. So that means that we have midpoints for both of those lines that are the same. So we have a parallelogram because they diagonals bisects. They have the same midpoint. Okay, so let's take a look at example number 5. So for this example, it says that we want to show that the diagonals bisect each other, which is exactly what we just did on page 4. So I want you to pause and try this example by yourself. So we're pretty much doing the same exact thing because we're showing that the diagonals bisect. So go ahead and pause your video, and when you come back, we'll talk about it. Okay, so we need to show the midpoint, just like we talked about on the other one. So for ZB, I get 3, 4. MO, I get 3, 4, so they bisect. Okay, so moving on to our last example, we want this one to show that they are perpendicular and bisect. So this time we have 2 line segments, perpendicular bisectors. So to be perpendicular, we need to show that they have the same slope. To show that they're perpendicular, and then we need to show that they have the same midpoint to show that they bisect. Okay, so go ahead and pause and try to find both those things. So find the slope of CD and the slope of AB, and they should be opposite reciprocals to make them perpendicular, and then find the midpoints of those 2 segments, and they should be the same to show that those lines bisect. So please go ahead and pause your video and come back, and I'll show you the work. Okay, so I hope you paused. If not, pause right now. Cheaters. Okay, so for AB, we get that the midpoint is 2, 2. Same thing for CD. So that means that they bisect. I did it backwards on this one than what we wrote on the one together. And then their slopes, AB is 2, CD is -1/2. So that means they're opposite reciprocals. So we have perpendicular lines. So they are perpendicular bisectors because they share a midpoint and have opposite reciprocal slopes. Okay, and that's it for 9.5 coordinate geometry proofs. So make sure you write down any questions you have, something you didn't understand, and we'll go over them in class together. Winner out.